Like announced. We have to do more work, like Pet Pen, Black Pen, Red Pen would say. Like announced in the last Putnam variant general BOI integral video, we're going to take a look at an interesting variant today. And I'm doing a big fucking recording session today, recording like 8 or 9 videos today. It's an absolutely great day for recording stuff. And yeah, we're going to take a look at this bitch boy right here. And it's just like the ones before, bloody amazing. So stay tuned for the final result. At first, I would like to turn this into the geometric series. So that's what we have done before already. So it's kind of the same as the integrals before, but we have to play around with the infinite series zeta function stuff in the end. So bear with me for a few minutes. At first, I would like to rewrite this as the integral from 0 to infinity of x to the s minus 1th power times 1 over e to the x plus 1. And the thing right here is, we can't really turn this into the geometric series at the moment because, well, negative e to the x is not in our radius of convergence at the moment, from 0 to infinity. Ain't working out so good. So what we have to do, we, well, have to make it work out. So why not advance this fraction by e to the negative x over e to the negative x to actually get an integral running from 0 to infinity. And the squid marquise is going down once again. X to the s minus 1th power. And then we are going to have e to the negative x over 1 plus e to the negative x integrated with respect to x. We are still not really done yet. Well, you can turn this into the Taylor series expansion for the geometric series, but what we can also do, we can kind of algebraic manipulate this right here to, well, just get rid of this e to the negative x right here. So that's what I like to do most of the time. So why not take a look at this differently? X to s minus 1th power. And what is this right here? Well, what we can do, we can add a 1 up here and subtract the 1 right again, because that's just a 0. And maybe you can already see why I'm doing this. Because if we break this fraction up, our numerator is additive, we get 1 plus e to the negative x over 1 plus e to the negative x makes 1 overall. And then we have negative 1 over 1 plus e to the negative x integrated with respect to x. That's an ugly looking d right here. That's the worst D I have ever seen in my life. Oh goodness, please don't demonetize my video, Google. Okay, we know how to work with this right here, so that's actually quite easy. What you can also do, you can factor out negative 1 if you want, but this right here is just a geometric series. So ending up with an integral from 0 to infinity of x to the s minus 1th power. And then we have 1 minus a sum running from. Okay. At first we have to turn this around a bit, because plus is nothing but negative times negative, because you have to have a negative sign in here for it to become the geometric series. And well, negative times negative works in fields. I've made a proof on that for the 5th time now. So sum running from k equals to 0 to infinity of, well, negative e to the negative x to the kth power integrated with respect to x. What you can do, you can get the first term to the outside, because then you are going to get rid of the 1 right here, because then we have e to the 0th power, negative e to the 0th power, but to the, yeah, everything is just 1, it's just 1. Take a piece of paper, try it out for yourself. You're going to get an integral from 0 to infinity of x to the s minus 1th power. And then 1 minus 1 is 0, but you are left with a sum running from k equals to 1 to infinity of, I'm going to put it like this, negative 1 to the, okay, this is kth power, to the kth power. Also, we had this negative sign right here originally, so if you bring it to the outside, you have negative 1 to the k plus 1th power. Let's put it like this. So let's get our order in the right place, let's put all the common terms together, and then we have e to the negatives integrated with respect to x. And now, once again, it's a matter of uniform convergence whatsoever to interchange this sum and this integral sign. It does work out. Try it out with Fubini also. No, this time you can't use Fubini because our integrand is strictly positive on this interval. Or is it? That's a good question. Leave some comments down below, my boys. Either way, I really don't give a shit anymore. So we can just bring this infinite series to the outside. K equals to 1 to infinity. Also, I'm going to bring this -1 to the k plus 1 power to the outside. And then we have an integral from 0 to infinity of x to the s minus 1 power e to the negative k times x integrated with respect to x. And just like last time, we would like to get our gamma function out of this whole bunch right here. So why not substitute t, for example, as being nothing but k times x, leaving us with dx being nothing but 1 over k times dt. We can plug in this chunk into here, so our up and lower bounds really don't change. Sum running from k equals to 1 to infinity of, this is -1 to the k plus 1 power. Also, we are going to get, I'm going to put everything on chalkboard right here. Why the hell not? We still have some time left. We have a lot of time left actually. I really don't have any time pressure right now. So we are going to get k to the 1 minus s power, t to the s minus 1 power, e to the negative t power, 1 over k dt. And just like before, 1 over k and this is going to cancel out. We can bring this k to the negative s to the outside, which is nothing but 1 over k to the s power. Okay, and also this integral right here, so this and this chunk is going to evaluate to gamma of s in the end. Okay, right now what we have is gamma of s times the sum running from, well, k equals to 1 to infinity of -1 to the k plus 1 power over k to the s power. And here's a little problem with this integral. Now we have this infinite series, and it's not really a Riemann zeta function, it's kind of an alternating Riemann zeta function, so we have to do more work, like Black Pen, Red Pen would say. Also, that's our integral I that we had in the beginning right here. Let's call this piece of crap I. Okay. I don't want to put something on the chalkboard which isn't an equivalence relation or something. Yeah, so we're going to play around with this infinite series a bit more. And let's write out a few terms and see how this actually looks like. Okay, we are going to concentrate on, let's call it capital S. We're going to concentrate on capital S. Okay, then we are going to get on the first term, that's -1 to the second power, -1 squared, which is positive, so this is 1 over 1 to the s power. Next term is going to be negative, it's an alternating series. 1 over 2 to the s power, plus 1 over 3 to the s power, minus 1 quarter to the s power, plus ... I really don't give a shit if you can do this in the normal case. If there are any restrictions on infinite series, something you have to be aware of. We are just going to algebraically manipulate this a little bit. So why not sort all the negative terms out? Let's bring them to the right side and all the positive terms to the left side. And I'm not meaning subtracting stuff. I'm going to put it like this. We have 1 over 1 to the s power, plus 1 over 3 to the s power, plus 1/5 to the s power, plus ... and then minus. Okay, those are all the positive terms, and you see those are actually odd. We can factor out the -1 on all of those. It's going to give us -1 over 2 to the s power, plus 1 over 4 to the s power, plus 1 over 6 to the s power, plus ... What is this right here exactly? Well, if we would factor out one more term, exactly 1 over 2 to the s power, then we are going to get, okay, this is -1 over 2 to the s power times, yeah, this is going to give us 1 over 1 plus 1 over 2 plus 1 over 3 plus ... Infinitely many terms of the form to the s power. To the s power, I'm terribly sorry. Because this right here, 6 for example, is nothing but 2 times 3 to the s power, and then you can distribute the s into everything. So you have 1 over 1 to the s power plus 1 over 2 to the s power plus dot dot dot. But this right here is nothing but the Riemann zeta function of s. So of the form sum running from k equals to 1 to infinity of 1 over k to the s power. Okay, this is nothing but the Riemann zeta function. Also, we could get our Riemann zeta function back once again, using this one simple trick that all mathematicians hate the most. What is we're missing for those odd terms to be the Riemann zeta function are actually just our even terms right here that we have left out. So why not add in between all of those 1 over 2 to the s power and plus 1 over 4 to the s power plus 1 over 6 to the s power. But also you can't just add stuff, you also have to subtract it. So also we have to subtract all those even terms that we have right here. Okay, so on the one hand we are going to get Riemann zeta function of s once again minus, okay, all those even terms. And those are exactly those of the form, okay, I factor out the negative ones that we have right here. So this is 1 over 2 to the s power plus, plus 1 over 4 to the s power plus 1 over 6 to the s power plus dot dot dot. Okay, I hope you can see where this actually came from. And well, what the hell is this right here? Well, we have derived it before. This is nothing but negative 1 over 2 to the s power times the Riemann zeta function of s. This is quite a mess, but I'm going to put our main results right here. I is now nothing but our gamma of s. And this infinite series right here is nothing but, okay, this is Riemann zeta of s minus 1 over 2 to the s power Riemann zeta of s minus 1 over 2 to the s power Riemann zeta of s. Okay, I'm terribly sorry, it's a bit cramped right here, meaning we have a common factor of Riemann zeta of s, so gamma of s times Riemann zeta of s, and then we have 1 minus 2 times 1 over 2s. 1 minus 2 times 1 over 2s. 2 to the s power. Yeah. And this is basically it. That's a lot of brain power I have to put out here to actually see through this shit. And I'm always hoping that I'm not doing any mistakes. By the definition of the Riemann zeta function, it's probably valid to do all those algebraic manipulations, probably because it's analytically continued or something like this. I really don't know, but it does work out. If you put this into Wolfram alpha, you are probably going to get this right here out. I thank the boy down there in the comments who actually suggested this integral to me. It was quite fun to actually solve it. It's a nice variant of the original generalized whatsoever integral. I thank you guys for watching. If you did enjoy this video, please like, subscribe, and recommend the boy if you like. If you want to support channel a bit more, you can buy those boyish t-shirts I created or support channel on Patreon. Up until next video, have a flammable dip. See ya!
Sehr gespannt, Musa. Und das wird ja nicht besser mit so Augen.
Ja, das fühlt sich schon ganz anders an. Das fühlt sich schon ganz anders an.
Das ist nicht ihr Schuh. Ah, ich kann es nicht sehen.
39 ist gut. 39 ist. Ne? Ja.